Today, we're going to finally learn the fundamental theorem of calculus, and this is going to allow us to see the difference or the connection really between indefinite integrals, so those were our integrals where we didn't have bounds, and definite integrals, and that's where we have bounds. Remember, so far when we've talked about definite integrals, we've said that this is giving us the area under a curve, and the only way that we know how to deal with these is a limit of Riemann sums. So we can write this as a limit as n approaches infinity of a sum from 1 to n of f of x sub I times delta x, which is really messy and not fun to try and calculate. So today we're going to see that there is indeed a connection between these two things. We're not just using the same notation for different things. And that's where the fundamental theorem of calculus comes into play. The fundamental theorem of calculus has two parts, and you might be thinking, well, Dr. Krager, we haven't done the first part yet. And that is correct. We are skipping to the second part of the fundamental theorem of calculus first, and then we'll go back in a couple days to the first part. So let's look at this. It says that if we start with a continuous function, then in order to find the definite integral of a function, what I do is I find an antiderivative of f, and then I plug in the numbers. I plug in the top number first, and then I plug in the bottom number, and I subtract. Okay, so let's see how this works. So the first thing that we have to do is we have to find an antiderivative of the thing on the inside. So an antiderivative of x squared is 1/3 x cubed. We can use any antiderivative. We don't need the most general one. We don't need the plus c on here, so we can leave it like this. Notationally, what I'm going to do now is I'm going to put a little angled brackets or a little thing like this. I don't know what you would call that. And I'll put the -1 and 1. The reason I'm no longer writing the integral sign is because we have anti-differentiated, so we no longer need the integral, but we still need to evaluate at these values. So that's what this is telling us. And so now the theorem up here tells me plug the 1 in first. So I'm going to plug in the 1 for my x's. So I get 1/3 times 1 cubed, and then I'm going to subtract what I get when I plug -1 in. So 1/3 times -1 cubed. So the first part will give me 1/3. The second part will give me minus -1/3. So that'll be plus 1/3. And so we're going to get 2/3 out. Let's think about what this tells us about my function. So this function x squared is always positive, and we're going from -1 to 1. So what this is telling us is that this area that I have drawn here, that area is 2/3. Okay, that's a lot nicer than what we've been doing so far. So the fundamental theorem of calculus is really our best friend. It's fundamental for a reason. So if we keep going, so I need to find an antiderivative of this guy. So that's going to be x cubed minus 1/2 x squared plus x. Again, I'm going to denote the fact that I still have to plug in the 1 and the 2. Notice it doesn't matter that what number is on top and bottom. We still always plug the top number in first. So I'm going to plug the 1 in first. So I'm going to get 1 cubed, which is 1, minus 1/2 times 1, which is 1/2, plus 1. I'm going to subtract what I get when I plug 2 in. Make sure you put parentheses around that because this whole expression needs to be subtracted. 2 cubed is 8. 2 squared is 4 times 1/2 is 2 plus 2. And now I have to do some calculations here. So the 2's will cancel each other out. I'm going to get 2 minus 1/2. It looks like I'm going to get 3/2 minus 8, which maybe is -6.5. It's okay to get a negative number out of an integral. If our function is totally positive, like it was in the first part, we should be getting a positive number. This function must have some negative values between 1 and 2, and so it's okay to get a negative number out. In a couple of days, we'll talk about what that negative number means. Okay, so let's see. To get an antiderivative of this expression, I need to simplify that first. So I'm going to distribute. So I'm going to get x cubed minus, this is x to the 1/2. X cubed times x to the 1/2. I have to add those exponents. So I'm going to have 3 plus 1/2. Let's see, that's 6/2 plus 1/2, that's 7/2. So I'm going to have x to the 7/2. Again, all I did there was simplify. I haven't anti-differentiated yet. So now if I anti-differentiate, I'm going to get 1/4 x to the 4th minus x to, let's see, 9/2 when I add 1 to 7/2, and I'm going to multiply by 2/9. Oops, 2/9 out front. And then I'm going to plug in the 1 and the 4. This is not going to be a pretty number. So I'm going to get 1/4 times 4 to the 4th minus 2/9 times 4 to the 9/2. Ooh. Minus, remember to put all of this stuff in parentheses, minus 1/4. 1 to the 4th will still be 1. 1 to the 2/9 will still be 1, or 9/2. So we'll just get 2/9. So I'm going to let you guys type that into a calculator. I got negative 49.81 out here. Again, we'll talk about what this number means in a couple of class periods. Okay, and one last problem here. So this is asking us to find the area. So let's graph cosine of x. Whenever we do trig functions in calculus, we should be using radian modes on our calculator. So just make sure your calculator's in radian mode. So cosine looks like this. It starts at 1, at pi over 2, it's at 0. So cosine is totally positive between 0 and pi over 2. So to find that area, I'm just finding the indefinite or the definite integral from 0 to pi over 2 of cosine theta d theta. Antiderivative of cosine is sine. And we have our bounds to plug in. So if I plug in pi over 2, we're going to have sine of pi over 2 minus sine of 0. Sine of 0 is 0, so this part will go away. Sine of 1/2 is, or pi over 2 is 1, so we'll get 1 out for that area. That was a really nice way to find that area. We didn't need any kind of approximation, and this is not a region that's a very nice region to work with.